Okay, so in this section, entitled Analyzing Graphs, we're going to be looking at functions defined algebraically, and then using skills that we've developed with the finding extrema values, with the first derivative, finding points of inflection and concavity with the second derivative, using limits to find behavior near asymptotes of graphs and behavior near infinity for graphs, and also finding x and y intercepts, which is not really a calculus question, it's an algebra question. So, features of a graph. The book has a nice picture here on page 433. A nice graph, and I think I'm going to use it because it has a little bit of everything. Okay, x and y intercepts. Okay, so x and y intercepts, remember, to get an x-intercept, this is the more complicated one to find usually. You set function equal to 0 and solve for x. Okay, so to find an x-intercept, set function equal to 0 and solve for x. And that's going to tell you, let's see, here's their graph they give us. Let's see, it does something like this, and then like this. And solving for the x-intercepts is going to tell you, I didn't draw quite exactly as they have in the book. It's going to tell you what these two positions are, where it crosses the x-axis, and of course the y-intercept usually is easier. So with the x-intercept you set the y value, the functional value, the output value equal to 0, and you solve for x. To find the y-intercept you set x equal to 0, the input, which is much easier usually. Because with a function, your function is written as, with that output variable, f of x, already explicitly solved for, right? So some function of x happening over here. So I don't have to say solve for y here, because y will already be, the output value is already solved for, it's already by itself, so I can just say and evaluate. Okay. And the y-intercept would be, of course, that value where the function crosses the y-axis. Okay, then we've got extrema. This is going to come from locating max and min. So how can I say? So that's where we use the first derivative. We say, where is the first derivative? 0. Where is it? 0. Also, where is it undefined? And that's going to tell us about maxima and minima. So one of the 0 spots, where the slope of the tangent line is 0, or the derivative is 0 on this graph, maybe right about there. There's a relative maximum there. Where is it undefined? Where is this derivative undefined? Here's a little point right there, a little cusp where it's undefined. And that tells us a little bit more about this graph. It tells you more than you would think too, if you really think about this finding extrema values. With this graph, if I had the function defined algebraically like this, and not a picture of it. And I found that there are these two extreme values here and here, and those are the only extreme values in this graph, then I know that this part over here doesn't go down and then turn back around and go up, because then that would mean there was another relative minimum down here. But I have all of the relative max and mins here and here. So I know that this function doesn't go and turn back around. So it's just going to keep going like that. And it's the same thing up here. I know that this isn't going to turn around and do something weird up here. Okay. Then we had points of inflection. That was what we just went over in 5.3. So I won't go into too much detail about that because we have all of that already. And those points of inflection are going to happen where the concavity of this graph is changing. So there is, well, the way they've drawn it, their graph kind of tilts here. So if you're looking at their picture, their graph kind of tilts a bit more. So they're saying there's a point of inflection there. But mine is pretty much concave down here. But I do have one here, over here, right near this x-intercept where my graph is concave down, but then it starts to be concave up. And I would say, just by looking at this, I would say it's not quite at that x-intercept, it's right about there. It's right about there, where the graph goes from having a downward trend to an upward trend. Okay, and what I will say about points of inflection is we used the second derivative. And it's really the same two questions. Where is it zero? Where is it undefined? Okay. The next two features of a graph we're going to use limits to investigate. So behavior near singular points. Now I should say this is behavior near singular points of the function, not of its derivatives or its second derivatives. Behavior near, thank you, the singular points of the function. And in algebra speak, these singular points could be asymptotes or holes in the graph, And to investigate behavior near these singular points, because singular points are points you can't plug into a function, like 1 over x, can't plug 0 in there, that's a singular point. So how do you investigate it? You use limits. You let the limit approach from either side of, towards that singular point. So in our picture, that would tell us the behavior near whatever this x value is right here, where the function is undefined for whatever reason. We can investigate the limit from this side, and the limit, both of these limits would tell us that the function was going up towards infinity, and that's what lets us know that both of these legs of this function go up and not one up and one down, or both down, or anything like that. It tells us, that's what the limit will tell us. And the final thing is behavior near infinity. Behavior So over here, this is behavior near an actual coordinate point, like an x value. So you're going to be letting your limit approach. The x value in your limit is approaching an actual number, like 5 or just 0 or some actual number. Behavior near infinity is going to be, you're going to use limits again, but this is where you're letting x go to positive and negative infinity. Positive and negative, it's separately, two separate limits, and that's going to tell you how the graph is acting out this way. So here it looks like this limit might be approaching kind kind of tending towards this x-axis, like the limit is tending towards 0, like there's a horizontal asymptote on this side. Whereas this limit is tilting down, this one looks like it's going off to negative infinity. Very slowly, but it is approaching negative infinity. In other words, there's no cutoff point where this thing is going to flatten off and approach a horizontal asymptote. Okay, so the whole point of all of this, though, is we're not going to be starting with a picture. We're going to be starting with an algebraically defined function. We're going to check all of these things, all 5 of these, and build the picture based off of this analysis of the function. So let's do some. And the book only gives us 2 examples here, and this is not going to be... for this week, you're supposed to look at 5.3 and 5.4. Your focus should definitely be on 5.4. This is a short section. I'm only going to work a few examples, and I'm not going to assign a lot of homework. But it's still important, but your focus should be on 5.3. Alright, let's start with their first example from the text. This is example 1. Okay, so this is a difference of 2 rational functions. Difference of 2 rational functions. You probably remember what 1 over x looks like. It's that it's got the leg going like this and the leg going like this, and 1 over x squared has a similar thing except both legs are pointing up. But when you start combining functions like this, their graphs just get crazy. So we cannot really use our knowledge of this function and this function to help us graph this function as a whole. So let's go through this process of finding first the x and y intercepts. So x-intercepts. Because you can definitely have more than one x-intercept. Alright, let's find these x-intercepts. So I'm going to take the function itself and set it equal to 0 and solve for x. Okay, first thing I'm going to do is multiply everything by x squared. That's to get rid of these denominators. By the way, am I allowed to multiply? Oh, never mind. Yes, this is fine. Okay, multiply by x squared on both sides. So 1 over x times x squared is going to give me x. And 1 over x squared times x squared is just going to be 1, and then 0 is going to absorb the x squared. There we go. So I've multiplied both sides by x squared. And this is super nice. Easy to solve, right? So it went from something that looked like, how the heck could we solve this for x, to this. There we go. Easy as that. Okay. What is the coordinate point then for the x-intercept? Well, the x value is 1, and we could plug 1 into the function to find out what the y value is. But remember, for an x-intercept, the y value is defined to be 0. Alright. What about the y-intercept? So I set x equal to 0, but that's a problem, right? F of 0, that's going to be 1 over 0 minus 1 over 0 squared. That's undefined. So, no. So there's no y-intercept. Okay. So we have one x-intercept and no y-intercepts. So how about I draw our graph so far over here. Now I'm going to cheat a little bit and take a peek at the end result so I know how big to make my graph. Okay, it doesn't need to be that big. So let's see, we'll call this number 1. And let's say 1, 2, 3. Okay, so all I know so far is that I've got an x-intercept at 1, 0. And I also know that this thing doesn't cross the x-axis anywhere else, and it doesn't cross the y-axis anywhere. So it's either all over here in these two quadrants, quadrant 1 and 4, or it's all over here in quadrant 2 or 3, or it's in both and it has an asymptote at this y-axis, maybe going up like this or down like this. Okay, next step. We found the intercepts. Let's find the extrema, meaning max and min, maximum and minimum values. Okay. That means we're going to need the first derivative. Okay. First derivative of 1 over x is going to be negative 1 over x squared, and then the derivative of negative 1 over x squared is going to be positive 2 over x cubed. So take a second, run the power rule, make sure you understand how I got this. Basically, what I'm doing is I'm writing f of x. I'm thinking of f of x as x to the negative 1, that's 1 over x, and then minus x to the negative 2. I'm thinking of f of x this way, and I'm using the power rule. Drop the negative 1, and then take it down by 1, drop the negative 2, and take the exponent down by 1. Okay. Now, what do I want to do? I want to say, where is this 0? Where is this derivative 0, and where is it undefined? Now, you can look at this, and you see it's undefined at 0, right? Undefined at 0 because of these x's. But the original function is not defined at 0, so there are no singular points in the derivative, for the derivative. So, that whole statement here, where's my pen? It's a long statement, so I'm going to write it in pen. F prime of x is undefined at x equals 0, but so is f of x, the original function. What does that mean? So, there are no singular points. I need to specify singular points for which thing. There are no singular points for f prime of x. Okay. I'm specifying singular points for, no singular points for the derivative, because later we're going to look at singular points for the original function. That's why I'm being sure to specify which function I'm talking about, the original or its derivative. Alright. Now, what about where this is 0? Because surely this can be 0 somewhere. So let's see what we get from that. I'm going to use a similar technique here. I'm going to multiply by x cubed on both sides to get negative x plus 2 is equal to 0. And then that's going to give me x is 2. X is 2. And now I need to find the y value of this coordinate point. So f of 2, not f prime of 2, right? F of 2, the original function. F of 2, that's going to be 1/2 minus, plugging into this function, 1 over 2 minus 1 over 2 squared. 1/2 minus 1/4 is 1/4. So I've got this coordinate point, 2, 1/4, but is it a max or a min? Is it a max or a min? I'm going to use the second derivative test. And the reason I want to use the second derivative test is I'm going to have to get the second derivative anyways to find the points of inflection of this function. So let me go ahead and get the, let's see, do I have room here? Yeah, I think so. So remember, the idea when you're checking one of these extreme values with the second derivative is, first of all, you got to get that second derivative. And then what we're going to do is once we have it, we're going to plug this 2 into this second derivative. And if it's positive, that means that the graph is concave up and that our point is a minimum. If it ends up being negative, that means that the graph is concave down and our point is a maximum. Alright, so I'm going to get the second derivative now, and that's going to be 2 over x cubed minus 6 over x to the 4th. So again, running the power rule with these, with these two rational functions, yeah. And now I'm going to plug in 2 and see if this yields a positive or a negative. So I'll have 2 over 8 minus 6 over 16. Let's see, that's 4 over 16 minus 6 over 16. This is going to end up being negative. So, graph is concave down. So, 2 comma 1/4 if it's concave down, and that point's right there where the derivative is 0, and concave down, that means is a maximum. We don't know, well, no, sorry, it should be is a relative maximum. Maybe it'll end up being absolute, maybe it'll end up being a whole absolute maximum for this graph, but I don't think so. I think we're going to have this function blowing up to infinity at one point. Oh wait, maybe not. Alright, let's see where we are with our picture. Where is my picture? There it is. Okay, so I've got my x-intercept already. I've got an extreme value at 2 comma 1/4, and it's a maximum. So here's 2, x value of 2, and up a little bit, right about there, somewhere at 1/4. And I know that this is a maximum, so on this side the graph is going to come back down. But it's not going to come down and cross the x-axis again, because I only have one x-intercept. I only have this x-intercept. So that means I know that this graph, since this point is a maximum, if I connect these, it can't keep going up because this point's supposed to be a maximum, at least relative to the points around it. So that means it has to go down past this point. But it also can't cross the x-axis, so it's got to be squeezed in between this point and the x-axis, so it must tend off towards infinity this way, just squeezing closer and closer to 0. But to be absolutely sure, I think we should get some more data. Okay. Alright, let's find the points of inflection. This is still number 1. Let's say POI for points of inflection. I've already got my second derivative, which is what I need to find my points of inflection. I need to set this equal to 0 and solve for x. I also need to ask where is it undefined, but the same thing's going to happen that happened with the first derivative. This thing is undefined at 0, but so is the original function, so there are no singular points for f double prime of x. So let's just set this equal to 0 and see what we get. See if we get some points of inflection. Okay, so let's see. 1 second. Okay, so similar technique for solving this. Multiply by x to the 4th on both sides. So that means here, here, and here. So this is going to turn into 2x minus 6 equals 0. 2x minus 6 equals 0, which is just going to yield x equals 3. So we have a point of inflection at 3, comma, and what is f of 3? What is f of 3? I'll do that off to the side. Okay, f of 3 is 1 over x minus 1 over x squared. So 1/3 minus 1/9, let's see, that's 3, so 2/9. So we have a point of inflection at 3, 2/9. Now, we don't know, we don't know if it's concave up or down at this point of inflection, or around this point of inflection. Or rather, what am I trying to say? Point of inflection is where it changes concavity from up to down or down to up. We don't know if it's concave up and then concave down, or concave down and then concave up. But maybe we do if we look at this picture that we already have. So we've got this point of inflection at 3, 2/9. So at x value of 3, and 2/9 is, let's see, 2 over 8. It's a little bit below 1/4. So roughly there. But we know that this is a maximum. So this point has to come down to this point here. So we don't need to do any testing around this point to see if it's concave down and then up, because we already know, let's see if I can use my pen for this, that this point here is a maximum. So this has to come down, meaning that this is concave down and then up, and then right here we need to know, is it supposed to continue going down, or does it go off to does it go up? But we already know that this point is supposed to be a relative maximum, so this has to, well, no, do we still need to? Oh no, I'm sorry. We still do need to check on the right side of it. We don't need to check the left side, because we know that this should be like this. But we do need to check this side over here to see if it curves down like this, or if it continues to curve down like that. Though, really, you could argue that it has to curve like that. To be safe, we can investigate just on the right side over here. So, on the left, we already know on the left at an x value of 2 that the graph is concave down. So we already know it's curved down there. And now what about on the right of 3, say at x equals 4? F double prime at 4. What is f double prime at 4? That's going to be 2 over 64 minus 6 over 256. So I'm plugging into the second derivative here. I want to test the sign of this to see if it's going to be concave up or down. And this is going to end up being positive. So concave up. So it goes from being concave down over here to concave up over here, which makes sense because it's supposed to be going like that. There we go. Alright. Next is, what is next? Singular points of f. Singular points of f. So we found all of our points of inflection. There was only one. Now we need to find the singular points of f. Alrighty. Okay. F is undefined. at x equals 0. So we need to investigate the limit as x tends to 0 from the positive side, and the limit as x tends to 0 from the negative side as well. Something we should note real quick. What I want to do with this limit is I want to use that technique where we just kind of investigated the growth of the numerator versus growth of the denominator. But in order to do that, I need this to be written as a single numerator over a single denominator, or rather as one fraction is what I'm saying. So we need to get this as one fraction, but that's easy. Just get a common denominator. It'll be x over x squared minus 1 over x squared. And then there we go, we've got x minus 1 over x squared. Okay, so this is the same as plugging in 0 from the right into this. So I can say 0 minus 1 over 0 squared. Now I should really point out that these values of x and x squared here, they're supposed to be coming from the positive side, right? So these need to be positive values because what's on the right of 0? Positive numbers, right? So the bottom is definitely going to be positive. 0 squared, or something positive squared is definitely something positive. And then this number here, whatever it may be, like 0.0001 minus 1, that'll end up being negative, right? So this whole thing is going to end up being negative overall. Whatever it ends up being, it's going to end up being negative. Unless it's just 0. It's not, but we've got positive in the bottom and negative on top, so it's going to be negative. And remember that when we have 0 minus 1 up top, it's just going to be 1, and 0 in the bottom. And remember that when we have a 0 in the denominator, this growth tending towards a very small number is going to give us overall behavior of this fraction of a very large number. So we're getting that as x tends to 0 from the right side, we're going off towards negative infinity. So as x tends to 0 from the right, we're going off towards negative infinity. Okay. What about from the left? Well, it's going to look similar, right? We're still plugging in 0, but now I need to think about, if I'm on the left of 0, these numbers are negative. This won't matter, though, because I'm squaring it, so that's still going to be positive. And this, a negative minus a negative, or a negative minus a number, it's just going to be more negative, so this is still going to end up being negative 1 over 0. And it's going to be the same thing, isn't it? Negative infinity. Negative infinity. So over here, as x tends towards 0 from the left, now I don't know anything else about this section of the graph, but I do know that there's no x-intercept, so it doesn't say start up here and cross the x-axis, right? Because this is my only x-intercept. So it's got to be down here. If it's going off towards negative infinity, it can't start up here because it would cross the x-axis. So it's got to be somewhere down here going off towards negative infinity. Alright, finally, last thing is to look at that behavior near infinity, well, as x tends to infinity. I don't have enough room here. Behavior near infinity. I'm going to say limit as x tends to infinity of f of x. That's going to be using the same setup for f of x that I had last time. Infinity minus 1 over infinity squared. Well, infinity minus 1, the minus 1 is going to be absorbed by the infinity. Now, where is the growth faster? in the top or the bottom? Clearly the bottom is faster, right? This is infinity, but this is infinity squared. So if the growth is faster in the denominator, then where are we going? If the growth is faster in the denominator... Oh wait, is this what I mean to say? Yes. Then we're going to have 0. Very large number in the denominator. So this would be like, 10,000 over 10,000 squared. This is going to get larger and larger in the bottom. This will never be able to keep up, and it's going to tend towards 0. So, as x tends to infinity, over here, which we kind of already knew that it needed to do that it needed to just get towards 0, just by using our inferences about this maximum value and the fact that there's no other maximum or minimum over here, so it can never turn around. There's no other point of inflection, so it had to be stuck right there in between the x-axis and this value. And what about the other side? Let's look as x gets very large to the negative direction. I'm going to have negative infinity minus 1 over negative infinity squared. Negative infinity minus 1, that's just going to be absorbed. That minus 1 is just going to be absorbed. Negative infinity squared is infinity squared. So this minus sign is going to stick around, but infinity over infinity squared, remember the growth is stronger in the bottom, so I'm just getting 0, so negative 0, that is meaningless, it's just 0. So as we approach negative infinity for x, this graph is trying to get very close to 0, but it can never cross, right, because there's only one x-intercept. So it goes like that, something like that. There we go. It's quite a process, but we just graphed this crazy function. Where is it? We just graphed this crazy function without really graphing any points. Like, we didn't do it numerically. We didn't make a big table of values. We just used all of this calculus and algebra for the intercepts to get a fairly decent graph of this function. Let's do another one. Alright, let's go with number 2. I'm going to go through this one a bit quicker. So let's say we've got a polynomial this time, and it's written this way, where it's partially factored, like this. Okay, let's find these intercepts. So x-intercepts. Alright, so we're going to set the function equal to 0 and solve for x. Product of two things equal to 0, so I can split them. This one is very easy to solve. X is 1, so there's 1. There's one x-intercept. Need to solve this. It's a quadratic, not easily factorable, so let's use the quadratic formula. So x is equal to negative 3 plus or minus square root of 3 squared minus 4 times a times c. All over 2a. And that's going to give me negative 3 plus or minus square root over 2 of 9 plus 28. 9 plus 28, that's 37. Alright, that cannot be simplified any further. So my two solutions here are, well, negative 3 plus or minus square root of 37 over 2. So my two x-intercepts are negative 3 plus square root of 37 over 2 and comma 0. And the other one is negative 3 minus root 37 over 2 comma 0. Alright, so I've got 3 x-intercepts. Let me go ahead and get the y-intercept, and then I'll work on putting these all on the graph. Now remember, you should only ever have at most one y-intercept. If you've got more than one y-intercept, that means that your function is not a function. You can still graph it like a circle or something like that, but it wouldn't be considered a function by the strict definition of a function, because it would fail that vertical line test. Alright, y-intercept. Plugging in 0, so f of 0 is equal to 0 minus 1 times 0 squared plus 3 times 0 minus 7. That's going to be negative 1 times negative 7, so that's 7. So there's my y-intercept, 0, 7. Alright, graphing these points. So my x-intercepts first, 1, 0, that's easy enough to graph, that's right there. Let's see, I could get these as decimal values. I'm going to say I know that square root of 37 is going to be really close to 6, because square root of 36 is 6. So you can run these in the calculator if it makes you feel better. Negative 3 plus 6 is 3 over 2. So I've got one at 1.5, which is like super close to the other one. And then I've got one at negative 4.5-ish, which is over here. And then I've got a y-intercept at 0, 7. So 1, 2, 3, 4, 5, 6, 7. Okay. 3 x-intercepts and 1 y-intercept. Now, in pre-cal, we investigated functions like this. If you recognize it, it's a third-degree polynomial, isn't it? And the sign up front is going to be positive, so it's going to have this overall shape, right, where one leg points down and the other leg points up. So if you remember that, then you know that this function should go sort of up through this x-intercept, cross back down, go through there, come through this other one, and then turn right back around and go through this one, and then go off to infinity. But the question is, exactly how far up do I go? Does it go up like right here and then turn, or does it go up super high, come down, and spike way down below and then come back up? So that's going to be, those were questions in 112 that you probably didn't focus much on. It was just kind of get the intercepts, get that end behavior, and then just kind of fill it in between. But now we have these new techniques that are going to let us actually answer those questions. Okay, so extrema. Take the derivative, set it equal to 0. Well, first I need the derivative. Derivative of this thing, it's going to be much easier if I just multiply this out, isn't it? Instead of having to use the product rule. So I'm going to multiply this out. So first let me say that f of x is, okay, x times all of this, that's going to be x cubed plus 3x squared minus 7x. And then negative 1 times all of this is going to be negative x squared minus 3x plus 7. Cleaning this up, I'm getting x cubed plus 2x squared minus 10x plus 7. Alright, I can easily take the derivative of this now just by using the power rule. So 3x squared plus 4x minus 10. Is that what I got over here? Yes. Okay. I want to set this equal to 0 because this is not going to be undefined anywhere. Right? There's no x in the denominator or under square root or anything like that. This is defined for all values of x. So I'm not going to get any weird extrema values at singular points for my derivative. But there are some places where this can be 0. And again, I'm going to want to use the quadratic formula because this is a quadratic function that I'm trying to find the zeros of. And I'm trying to make this video not super long, so pause the video, go run the quadratic formula, and you should end up with negative 2 plus or minus square root of 34 over 3. These are not x-intercepts, right? But these are extreme values, max or mins. Okay. So my first possible max or min is negative 2 plus root 34 over 3, comma, oh, I don't know the y value for the actual function. I don't want to put 0 here, right? Because I want to plug this into the original function, or this version of the original function. So that's going to be quite a nightmare to plug this into that, or even this into the way it was written originally. So let's see, I know I calculated it earlier. I'm just going to tell you what it is to save time. This one is negative 0.426. So I plugged it into the calculator to get that. Plugged this into f of x. The other one is negative 2 minus root 34 over 3. And that one gave me 28.945. Okay. Is this a max or a min? Is this a max or a min? Well, let's get the second derivative so we can figure that out. Is that going to be the easiest way? Yep, I think that's going to be the easiest way. Alright, f double prime of x is going to be 6x plus 4. I will want to set this equal to 0 and solve when I'm finding the points of inflection, but right now I'm still trying to figure out if these are max or mins. So what I want to do is say f double prime of negative 2 plus root 34 all over 3. Does that yield a positive or a negative? In here, let's see, that's going to be positive. So that means it's concave up. So this point, if it's concave up, I'll just say is a minimum. Min. So the point negative 2 plus root 34 over 3, comma, negative 0.426 is a min. Oh goodness, I can't spell today. Okay, check the other one. F double prime of negative 2 minus root 34 over 3. Blah blah blah, plug that into the calculator. We get negative. I don't care what the actual value is, I'm just trying to see if it's positive or negative. So this is concave down. So it's a maximum there. So that means this point is a maximum. Okay. Which again, if you already know about the behavior of this x cubed graph, then maybe you could have inferred that this would in fact be a minimum and this would in fact be a maximum, just by looking at where these x values fall on the graph. Alright. What's next? Points of inflection. That should be super easy relative to how nasty all of this was to plug into the calculator. We're going to set f double prime of x equal to 0 and solve. Whoops. And that's going to give us negative 4 divided by 6, negative 2/3. Negative 2/3, and is it, what is the coordinate point for that? The y value, plugging in negative 2/3 into the original function, gives me 14.259. So that's going to be a point of inflection where it turns from being either concave up or concave down to concave down or concave up. We're not sure yet if it's up then down, or up then down, or down then up. So how do we check that? Well, we want to check the sign of something that's on the left and right of negative 2/3. So why don't we just pick f double prime of -1, f double prime of 0. Well, f double prime of -1 is definitely going to be negative, so that's concave down on the left. F of 0, or f double prime of 0, is just 4, which is positive. So we're getting concave up. Concave up. So that means that... Oh, I didn't graph my extreme values. Let me do that real quick. I've got a minimum at this. Oh god, where even is that? What is the x value for that? Alright, so this x value is 1.277, and hang on. Alright, the other one is -2 minus square root of 34 divided by 3. Negative 2.610. Alright, so those two extreme values, one at 1.277, so that's a little bit past 1, and it's negative, oh, it's right in there, right, somewhere right in there. That's my minimum, and then my maximum at x value of -2.6, which is going to be, here's -1, -2, so somewhere right in here, and all the way up at almost 29, which I think my graph went up to 27 or 28, so I need to go a little bit beyond. So all the way up here, all the way up here, and so all the way up there somewhere. That's roughly it. And then I had a point of inflection. So I know that it's concave down on the left of my point of inflection and concave up on the right. So it's at -2/3, comma 14. Let's see, this is 7, 8, 9, 10. Was that 7? Yes. 8, 9, 10, 11, 12, 13, 14. So at 14, a little bit past 14, oh damn it, 10. And not quite out to 1, so roughly there. That's where my graph goes from being concave down, now being concave up. I don't have any singular points to look for in the graph of my function, so there's no asymptotes or anything like that, no singular points. Or I guess I should say singular points, none, there we go. And then behavior near infinity, this should be quick and easy. The limit as x tends to infinity of f of x. Well, if my function is positive x cubed, that's the leading term, and I plug infinity into that, I'm going to get infinity cubed. So that's going to be infinity. So it goes off towards infinity as x gets larger. And what about as x tends to negative infinity of f of x? Well, if my leading term, the strongest term, is x cubed, and I'm plugging in negative infinity, that's going to be negative infinity cubed, which is going to be negative infinity, right? Negative infinity. The point is that since it's a cubic function, that negative being plugged in comes back out, and it does end up being negative, which we already knew. If we already knew it was an x cubed function, then we knew as you let x get very large, towards the right it goes up, and towards the left it goes down. Putting all this together, ooh, I'm gonna have something like this. Going up, hitting that point, coming down, there's the inflection point, so it's starting to become more concave up, going through these, and then something like that. There we go. Alright, last example. This is example 2 from the text. This crazy function. Alright, 2x over 3 minus x minus 2 raised to the 2/3 power. Recall that that 2/3 power means, I could rewrite it as 2x over 3 minus cube root of x minus 2 all squared. That's what that 2/3 exponent means. Since we're going to be taking derivatives, this format's going to be much more efficient, useful, since we're going to be taking derivatives of this function. Without this piece here, this is the crazy piece, right? Because this is just a linear function, slope of 2/3, right? That's all that is. This is a very nicely behaved function, but this is a bit weird. Putting them together is going to get even weirder. Alright, intercepts. X-intercepts. Let's set this thing equal to 0. Set this thing equal to 0. What can I do? What can I do? I'm going to cube both sides. Because that... Oh, wait. Is that what I mean to do? No, that's going to make things... No. Oh, I know what I'm trying to say. Sorry. First, I'm going to add that piece over, so 2x over 3 minus... Alright, add that piece over, so I'm going to have 2x over 3 is equal to x minus 2 to the 2/3. Now raise both sides to the 3rd power. That's going to have the effect of getting rid of this 3 in the denominator of that fraction. This needs to be cubed. That's going to be 8x cubed over 27, and then equals x minus 2 squared. So I'm going to end up with this crazy cubic function here. I'm trying to save space, so let me work this way. So 8x cubed over 27 is equal to x squared minus 4x plus 4. Scoot everything back across the equal sign to get it back equal to 0. So I'm going to have 8 over 27 x cubed minus x squared plus 4x minus 4 is equal to 0. So I'm supposed to solve this cubic function for 0. You may have learned the rational root theorem in pre-cal last semester, or whenever you took pre-cal. Something called the rational root theorem, but that only works if your function has rational roots, and in fact this one doesn't. If it doesn't have rational roots, or if the rational root theorem fails, and you can't factor this thing, you've tried synthetic division, everything is failing, you really do have to use technology to help you solve for, unless you want to use the cubic formula for polynomials, but that is a nightmare. So we're going to cheat a little bit. I think the book cheated a little bit to do this too. And we're going to use technology to help us solve for the x-intercepts of this thing. And we're actually going to find that there's only one, and it's approximately 1.244. So we're getting a x-intercept at 1.244, 0. Alright, and the y-intercept, so I'm going to plug in 0, so f of 0 is equal to 2 times 0 over 3 minus 0 minus 2 raised to the 2/3. That's going to be 0 minus negative 2 raised to the 2/3. That's the same as 0 minus cube root of negative 2 squared. So that's going to be the same as 0 minus, so let's see, squaring that's going to be a 4 in there, so we're just going to have negative cube root of 4. And that is approximately... I don't know. That is approximately negative 1.587. There we go. So that's our y-intercept, 0, comma, negative 1.587. Okay, so for my graph here, let's see, y-intercept at negative 1.587, so that's roughly there, roughly. My one x-intercept is roughly there. Alright, that's all I've got so far. How about extrema? So I need to take the derivative of this function. What is that going to be? 2/3. So taking the derivative of this part will just give me 2/3, and then minus, okay, chain rule happening here, derivative of the outer with respect to the inner. So I'm going to drop that 2/3, becomes a coefficient. Copy the inner function and take this down by 1, so giving me negative 1/3. And then I multiply by the derivative of the inner, but the derivative of the inner function is just going to be 1. So it has no effect. So there we go. Okay. Now, this function, by the way, can be written as 2/3 minus 2/3. There's the 2/3, this 2/3. And x minus 2 to the negative 1/3 power, that is the same as the cube root of x minus 2 in the denominator there. So we can see by looking at this, looking at it in this form, that f prime of x is undefined at what x value? What x value is going to give us a 0 here in the denominator? 2. It's undefined at 2. So we have a singular value. We have a singular value at x equals 2 for our derivative, meaning that there's a sharp point there that has the potential of being a max or a min. Let's go ahead and get that point. It's for the actual function itself. It's going to be 2, 4/3, plugging into the original function to get that. Is that a max or a min? I don't know. Not yet. Where is f prime of x equal to 0? Minus 2 over cube root of x minus 2. Whoops, didn't need that parentheses. Equals 0. Where is this thing equal to 0? Well, oh my goodness. Add this part over, so I've got 2/3 is equal to 2/3 times the cube root of x minus 2. Oops, no, not equals 0, equal to each other. Divide by 2/3 on both sides, and I'm getting 1 is equal to 1 over cube root of x minus 2. 2/3 are canceling each other out here, just getting rid of those coefficients. They're exactly the same. So, alright, now multiply by cube root of x minus 2 on both sides to get it out of the denominator. Okay. Cube both sides, and I'm getting x minus 2 is equal to 1, because 1 cubed is still 1, and then adding 2 to both sides, I'm getting x is equal to 3. So I've got another possible max or a min at 3, comma, and then the y value will come from plugging in to the original function. What is that going to be? 1? Yes, 1. Alright, so max or min, max or min, max or min, don't know yet. But if I get the second derivative, I can use the second derivative test. So let's get that, the derivative. So I'm taking the derivative of this now, of the first derivative. Can I get them both on the same page? There. This will go away, just becomes 0. Then negative, and I want to drop, I want to take the chain rule. So I'm going to take the derivative of the outer function with respect to the inner. So this is going to come down and multiply onto that. So that's going to end up being positive, negative times negative, 2/9, and then times x minus 2. And then I'm taking this down by 1, this exponent down by 1, to be negative 4/3. So there's the derivative of the outer with respect to the inner, then times the derivative of the inner, but remember the derivative of the inner is just x minus 2. That derivative is just 1, so that part has no effect here. So I'm just getting 2/9 times x minus 2 raised to the negative 4/3. Okay. Okay, so if I check this point, f double prime at 3, so I plug 3 into this, and that's going to end up being positive. So that means it's concave up. If it's concave up, that means that point is a minimum. Now, what about f double prime at, wait, what was the other value? 2. That's the other one I want to check. But that gives me undefined. If I try to plug 2 into this is in the denominator, right? This is a negative exponent. This is the same as 2 over 9 times the cube root of x minus 2 to the 4th. So if I plug in 2 here, I'm getting a 0 in the denominator. So I can't use the second derivative test on this point. I would have to test it some other way. But let's see where we are now. Maybe we don't need to test it some other way. Maybe we can just make some inferences from our graph to see where we are. Alright, so I know I've got a minimum at 3, 1. A minimum at 3, 1. That's a minimum. And I've got another point at 2, 4/3. 2, 4/3 is right about there. And I don't know if that's a max or a min yet. Okay. But I think if we figure out what's going on with the points of inflection, we might be able to see what's going on here with this graph, with what's going on in between. So I'm trying not to have to do a bunch of test points around, because test points are annoying, so let's see if we can get away with not doing test points. Points of inflection, though, that's going to actually be a problem, because that's when you want to take this second derivative set it equal to 0 and solve. But you see, this is not going to have any solutions. There's nothing, if x is in the denominator by itself here, and you're trying to set it equal to 0 and solve, there's no solution. There's no value of x that you can plug into a denominator that will give you a 0. You can make it undefined, right? I can plug a 2 in here and make the denominator here 0, making this undefined, but I can't get a 0 in the top, right? There's no way to get a 0 in the top, so there's no solution. This means there are no points of inflection. Alright, so let's see what we got here. No points of inflection. That means it's always concave up or concave down. Or like a straight line. But surely we know this function is not a straight line. Alright. So this is either always concave down or it's always concave up. What else do we know, though? We know that f prime at x is undefined at x equals 2. This is a cusp. This is a sharp point, right? This is a sharp point. And we know that if it's a sharp point, this graph can't be going up there's no asymptotes in between. It can't be going up and then maybe like spiking and coming back down here and doing something weird, because we didn't find any maxima in here, and we know it doesn't blow up to infinity in between here because we didn't find any singular points in the original function. This is the original function. This function is defined for all x values. The original is. Its derivatives are not. So we know that this is a cusp, and since we know that it doesn't go up, blowing up towards infinity or another maximum point in between these 2 points, that it has to be a maximum. And since it's a cusp, we know it's shaped like that. But that tells us that we also know that this graph is concave up or concave down everywhere. But if this is a maximum and it's a cusp, then it has to be concave up around the cusp. That means this graph is going to be concave up everywhere. So it's going to do something like this, concave up, hits that cusp, and then it's still concave up. And remember, this is supposed to be a minimum. This is the 3, 1, so it does something like that. Now, we don't know about the end behavior yet, so let's investigate that now. In fact, I'll just do it on this paper here. So the end behavior, behavior near infinity. Limit as x tends to positive infinity of f of x. Oh. 1 second. Okay, so we could say this is 2 times infinity over 3 minus infinity minus 2 raised to the 2/3. You know, we really don't need to do this, though, because we know that the function is not going to turn around. We know it's concave up everywhere, right? So it could possibly maybe like do this, but we would find if it did that, there would be another extreme value, another minimum. So we know that it has to just keep going down and never turn around and gain another minimum value. So it has to do that, but how would that work here? Well, we would have two times 2/3 of infinity. Yeah, this is going to get a little weird. 2/3 of infinity minus this -2 in here isn't really going to matter that much. The addition and subtraction from infinity doesn't matter much. It's the multiplication that has an effect, and negatives. So infinity to the 2/3. And then it's a question of, is this one stronger or is this one stronger? Because that's going to determine whether or not we're going to get positive or negative infinity here. And that is a good question. You would need to, let's see. This is a case where L'Hopital's rule could be useful, but I really don't want to go through all that because we really know just by making inferences from our previous data that this is going off towards negative infinity. So in fact, this one has to be stronger. And to really prove that, though, you would want to go back to the original function. No, not L'Hopital's rule, sorry, but it is in indeterminate form, so we would need to do some algebraic manipulation to this function to really get down to this answer. But based off of our previous data, we know that it's going off towards negative infinity. What about the opposite direction? I'm going to have 2 times negative infinity. It's going to come down to a similar question. This is going to be equal to negative 2/3 infinity, and then minus 2 doesn't matter. Thing is, actually, though, we're going to have negative infinity to the 2/3, but you're squaring, that 2 means you're squaring this, so we're getting similarly infinity to the 2/3 there. Or well, it's negative, and that's going to mean this, because that negative inside is going to get absorbed by the square. So this is surely going to be, oh, sorry, no, what am I saying here? This is going to be, oh, dang it. Okay, I just realized I got this all mixed up. This, oh man, I'm getting high off this Sharpie. God, okay. Limit as x tends to infinity. This is going to be positive. That's this side. Jeez. X minus 2 to the 2/3. This is going to end up being positive infinity. It's blowing up towards infinity that way. But again, we know that because it's concave up, and it's never going to turn around. If it turned around, it would end up being concave down, and there would be a point of inflection, or there would be some kind of max or min value there. So we know that it's always going to be blowing up towards infinity, meaning that this is actually stronger when I'm setting this up. And then here, as x tends towards negative infinity, we're getting the 2, oh my god, f of x is equal to 2 times negative infinity over 3 minus negative infinity minus 2 to the 2/3. That's going to end up being negative infinity. That's on this side. That's on this side. But you'll see the book didn't even talk about this because they say, there's no more inflection or max and min points over here, so it's just going to go off to negative infinity and positive infinity. Alright, that is it for this section, and I'll post the homework as text in the actual discussion itself.